So my name is Fedor, and I'm the chief scientist. Half of my time is spent actually doing coding. And most of the other half is either education of engineers who work for me, or doing software design, software architecture. So I put a lot of thought into how we do the design and why, and design patterns come up in that work. So we're going to talk about design patterns, but we're not just going to talk about design patterns. There is a twist to this. First of all, I have to tell you what design patterns are. So in software specifically, it's a repeatable, commonly recognized solution to a commonly occurring problem. It must have, in order to really be a design pattern and derive all the benefits we want to derive from design pattern, it must have these attributes. It's a design problem, it must be commonly occurring, and it must have a widely accepted solution, including known advantages and disadvantages. So you'll see why those things are important, but what it also shows is design patterns have their own life. In particular, the last two items, new things emerge, people start disagreeing about what's the commonly accepted best solution. Some of the trade-offs go away, some of the trade-offs reappear. Design patterns emerge, they live, and sometimes they die, or at least fade off. They're not designs themselves, they're kind of design templates, guidelines for design. But the second aspect of it that is also very important, we're not going to be talking about it today, but it's very important for you to understand. They're very compact, expressive vocabulary elements. If I say to you, we're going to use policy-based design, well, I just told you a whole lot about what we're going to do. You already have an image forming in your head. And there is a reason why they are this way, and to kind of give you a different angle on this reason, I have to go back to where they came from. So everybody knows the Gang of Four book, which largely defined the way we think about the patterns. The concept of the patterns actually came from architecture, of all things, about 20 years earlier. In software, they were introduced about 10 years before the Gang of Four. But that concept in the architecture itself came from the idea of archetypes. Just like, if you read a story and you recognize, okay, this is a warrior priest, you have a mental image about where that character is going and what's about to happen to him. Same in design patterns. It's very compact, very powerful way of communication. The book did form the way we think about it. It didn't end the way we think about it. Hopefully, we still think about the patterns, which means there are more than the original 23 patterns, and there are more than object-oriented patterns. Should you use design patterns always? Well, patterns are very general design principles. There is always an exception, but honestly, this exception probably doesn't apply to you. Everybody thinks they're special, everybody thinks their case is different. Really, it probably isn't. And if it is, it's probably not worth the time and effort and the bugs you'll make to do a special case for your special case. So it's kind of 1% of the 1% is when you actually have to do idiosyncratic solution. On the other hand, not every problem has a design pattern for it. There are new problems. There are cases where there isn't a common agreement on what we should do. So it's not like there are design patterns everywhere, but established design patterns, please try to use them. They're commonly accepted for a reason. Do the design patterns depend on the language? Well, at the high level, the answer is they transcend the language, they're design elements. Sure, some languages are more suitable for some patterns, and some languages create problems that call for some patterns, but for the most part, they shouldn't. And that's true as far as it goes, but it misses another point. So design, you can design software and then write the whole code in assembler. If you have enough mental discipline, it will be perfectly organized and well-structured. Yes, you can do it. It's hard to keep yourself from doing evil things, but yes, you can do it. But it's a different question from, does the language development, the language evolution, affect how we use the patterns? And it boils down to small stuff, because patterns some of them are easier to use in some languages, some of them are harder, and then the language changes. This low-level friction changes. It's small things, it's annoying things, it's a copy-pasting, it's boilerplate code, it's limitations in the language. None of this is fundamental design constructs. But it's a friction that keeps you from using certain pattern and steers you to a design to your software differently. As the language evolves, some things become easier, some things become significantly easier. If one of the patterns suddenly became almost frictionless, and you realize that, it may actually prompt you to change the way you design. And that's really what this talk is about, that evolution makes kind of all things more or less better, easier. We try not to screw up our languages with new features, but there may be a tipping point which would prompt you to reconsider the design pattern that you're using. I'm not going to have time to actually show you any of the patterns themselves in a lot of details. There are lots of books on patterns. Everybody has a book of patterns. Even I have a book on design patterns. That's mine. There are many others. The patterns that I am going to show are examples of design patterns. I picked them to show different ways patterns evolve when language evolves. There's nothing more to it. If you want to learn about a particular design pattern, well, first of all, there will be some slides which show more of the implementation that I'll skip during the talk. But they are in the slide deck. You can go back to them, and you can see the implementation, the guts of it. And that may help you a bit. And if you want even more details, well, look at one of the books that has that pattern. Let's start with a builder. Builder is a kind of pattern that has a fairly normal evolution in C++, so I want to show you basically how a pattern evolves in C++ if nothing dramatic happens to it. It's a creational pattern used to create objects. In particular, it's used to create objects that are difficult or cumbersome or complex to create. If you look at the description, it separates the creation of the object from the representation. And yeah, that's technically what it does. Usually you fall to builder, you start using it if your creation of the object is complex. It's not that you have to, but that's mainly what the common use. So, okay, this pattern is not in my book. It's in Dmitry Nesteruk's book on C++ design patterns. So that's where I've taken this one.
So are you using this synonymously with factory then?
No, there is a difference between the builder and the factory, and it would take me half of this talk to talk about it. One advantage is we're not limited unless you have. We don't have another talk afterwards. So if you want to talk to me, I will be available. But it's a long conversation. Here is some HTML element, and it has a name, and it has a text, and it has children elements. And that children elements is what makes it difficult to construct because there is a lot of stuff you can shove into that vector. And there is already a hint here that there is a builder coming up. So that, I'll just use this pointer so everybody can see. Friend class HTML builder. Well, so there will be a builder coming up. Now, the normal presentation I would show you the builder first. I'm trying it the other way. I'm trying to show you what the client code looks like. So if we got this pattern, we did it, this is what the client code would look like. Then you can figure out how to implement it. I'll have some hints. Implementation isn't particularly important. The use of the pattern is interesting. There are, 10, maybe 15 ways to write a builder in C++. I'll show you this one. It's called Fluent Interface. What's interesting about it is see the way the function calls are chained. Builder, it'll create an element UL. There is no text, just the name. And then I'll add one child, and I'll add another child, and I can keep adding those function calls. Some languages have this feature called method chaining, which is actually just calls member function after member function on the same object. C++ doesn't have that, so you can't do it in C++. But if you can't do something, but you really, really want to, you sort of can. So you'll see how it's done. It's also used, by the way, to give named arguments in C++. Another thing, in C++, functions have positional arguments. You can't have named arguments in C++. But I really, really want to have named arguments. That's how they look like. If you want to know the implementation of that, that won't be in my talk, just ask me. Or that one actually is in my book. Okay, so the juice behind the method chaining for the builder class is very simple. Just returns the reference to itself, which means I can keep calling member functions on it. That's how you do method chaining in C++. So other than hooking up for method chaining, what does it have? Well, it takes the name and a text and it constructs the HTML element and pushes it back onto the child element, and that's the builder. So that was C++3. What does C++11 bring to the table? Nothing really earth-shattering. Yeah, your normal things. You have them in place. You have the forwarding references. Makes some things a little easier. You have the for loop to iterate over children if you need to. This is the normal evolution of a C++03 program into C++11 program. This is what you would expect if you took a C++03 program and started improving it using the new features. It does have even this pattern actually has a variant, and that's the second reason I'm showing you. In addition to giving you the normal improvement of C++11-14, reduce the friction of using the annoying stuff from 03. Some of the annoyances are less annoying now. It creates a new variant. You can write in C++11. You can write a builder like this. So now all the HTML elements have their own names, and the child relationship is just shown by nesting, and you can keep nesting it forever. By the way, if you have questions, I'll be here after the talk for as long as you want me. So just remember the slide number and ask me questions. If there is something like egregiously wrong on one of my slides, something that would confuse everybody else except you who noticed it, let me know. So how does that builder look like? Well, first of all, let's see what's not here. Friend HTML builder is not here. The builder class is actually gone. Well, it's not quite gone, but I didn't have to write it. You'll see where you will kind of see where it appears. This vector of children is populated from the third constructor argument, and I'm going to move the argument into the children. We'll see why move in a moment. So my concrete classes now define the grammar. Where is the actual builder class? Well, the builder class is kind of hidden. Here's my concrete class, UL. It takes children, the name is fixed, the text doesn't have a text. The children are in this initializer list. And I'll construct the vector from the initializer list, and then, it's a temporary of course, and then I'll move from that vector into where it lives permanently. So where is the builder? Well, it kind of peanut buttered over that initializer list and the vector construction. So basically the C++ template generation mechanism synthesized the builder code for me. There is no builder class here. I got the template, the compiler to generate the builder for me. Now this, I have to show two elements because I used li also. This time I need the text, so I have to pass the text argument to the constructor. No? Unfortunately, no. Standard initializer list has to be the only argument. Well, there could be arguments after it. It can't be before. If you can't, but you really, really want to, you sort of can. You have to convert the parameter pack into the initializer list, and that's how you get initializer list at the end of your argument. So I really want to have this. I have to do this. Okay, so to summarize this section, here is a pattern that wasn't particularly annoying, became a little bit better because your regular improvements move and in place and all that stuff, but at the same time an entirely new version of this pattern emerged with the new features. And we're going to see that that's going to be pretty typical. I've shown you this as a kind of baseline. This is a pattern that wasn't too bad, didn't become earth-shatteringly good, and had a new twist on it. So now we're going to see something else. We're going to see deviation. So there are lots of other patterns, and they're all kind of like that. There are deviations. I'm going to show you some of the deviations, not all deviations. There are some deviations. Well, visitor. Why visitor? Well, if you have a C++ talk on design patterns and you don't mention visitor, that's sacrilege. So that's reason number one. And two, it actually does have some interesting evolution with language that I'm going to show you. What does the visitor do? Okay, anybody here doesn't know. I mean, visitor is a very old pattern. Anybody here doesn't know what the visitor? Don't has. I'll go through a few slides to explain it. So if you need, let me know. No, honestly, so it's okay. So nobody needs it. Okay, I'll go through the introduction. But if you need, ask me and I'll go through the slides. In one sentence, you can add new, as if you added new virtual member functions to classes without modifying the class. That's basically what Visitor lets you do, in one sentence. So I'll skip this. Why would you want to add new virtual member functions to classes without modifying classes if you could just add new virtual member functions to classes? Well, one, maybe you can't modify the hierarchy, public API. Two, and that's actually a different case, you want to keep decentralized decision making. An example, you have serialization. Actually, the serialization visitors are pretty common in application. So each class knows how to serialize itself. Well, how do you serialize a class? You serialize all of the data members one by one, and when you get down to built-ins, you serialize those, again, one by one. So my vector serializes itself by serializing every element on the vector. Each of those serializes every data member, and so on. That part, the class knows. But what do you actually do with the bits? Well, maybe you write them to disk. Maybe you write them to the socket. Maybe you store them somewhere. The serializer knows that part. How do you bring all this knowledge together? How do you actually do serialization? Option one, you write a huge function, centralized, with a double nested case statement. And that's where you make all the decisions. Yuck. And option two, you do the visitor, where your final code that actually will run is selected based on two things. Which class I'm serializing, and how I'm going to do serialization. These are not the only two options, but visitor is a good option for this. I'll show you a classic visitor in C++03 now. I have a class hierarchy. I have my pets, cat, dogs. For some reason, whoever implemented the pet hierarchy forgot to feed them. So I don't have a feed virtual function in the class hierarchy. I have to add a feeding visitor. I'll jump straight to the client code. This is how your code will look like after everything is said and done. You create a cat, you create a feeding visitor, and cat accept visitor. Why is it called double dispatch? Well, this code will end up in some function that depends on two parameters. What is the actual type of the pet object, C, and what is the actual type of the visitor? That's why double. Well, dispatch is just simply I'm directing the execution somewhere. Double, because there are two types that affect it. That's all. Okay, we're still in C++03, which means, yeah, it's going to look kind of annoying. Class hierarchy, which means I have a base class, and I must add, in order to make my hierarchy visitable, I must add this virtual accept function. It accepts the visitor. That's all I have to do. So if my hierarchy wasn't visitable originally, yes, I have to modify it once, but once. After that, it becomes visitable. Okay, my classes, cat inherits from pet, dog inherits from pet. Pure virtual, which means I have to override it everywhere. I can't forget, the compiler won't let me. And they all look exactly like this. What accepting a visitor means telling the visitor to visit myself. Copy paste over and over again, but it has to be in the derived class because it's an override of the virtual function. And again, I have some pet, which is the base class pointer. I tell it to accept a visitor. The accept call ends up here. It's a virtual call. Visit is also virtual, so the second virtual call, and that's how double dispatch works. I did first dispatch was depending on type of P, second dispatch depends on type of V, so I got to some place that depends on both. How do you actually write it in C++03? Well, you have to create overloads for the visit for all of the types you want to accept. It's overload resolution, there's nothing interesting here. And here is your base class, virtual functions. Here is your concrete class, derived. Okay, if we're visiting a cat, we're going to feed him some tuna. Well, dog is lucky today, getting good food. Here's how the client code looks like. We have lots of different visitors, so we can add multiple operations to our hierarchy. Whoever wrote the hierarchy really didn't like pets, didn't bother to add any of those things to the interface. No problem, we can do it with the visitor. So what's good about the visitor? Well, you can add new operations without modifying the hierarchy. What's not so good about it? Well, if you add a class to the hierarchy, you have to update the visitors because the overloads must be updated. Visitors unlike virtual functions, don't have access to private. You may have to sacrifice encapsulation, so you can read about other trade-offs. So that's what good and bad about Visitor from the design point of view. Now, what's annoying about Visitor from the implementation point of view? Mainly all of that boilerplate code. You have to write that accept member function, which looks exactly the same, and you have to write it in every one of your classes. And you have to write the visit function that looks, well, the declaration looks exactly the same, the body looks different every time, but you have to write those visitors somewhere up there, their classes, and then in your client code down here, where the call actually occurs, how do you know what it's going to do? Which file am I visitor again? Scroll, scroll, scroll up. Okay, here is the visitor, here is what's actually going to happen. A lot of friction in the visitor pattern. None of it is big. None of it that you can't overcome. You do it day over day over day, it gets old. What do you do if you have access to the modern C++? Well, you still have your class hierarchy, same as before. Once per hierarchy, you write this visitable template. And then you derive everybody from that visitable template, and what does it do? Well, it takes the derived as a parameter. So now it can synthesize the accept functions by template instantiation in the derived class now. You can't put them in the base class. You have to put them in the derived class. Nobody says you have to code them yourself. Template instantiation can do it for you. But this here, this line, that's a C++ 11 thing. So you couldn't do it in C++ 03. So in C++ 11 and above, you can simplify some of the boilerplate. If it looks similar to the curiously recurring template pattern, it is similar, but not exactly the same. Okay, so item 1, we can reduce a lot of boilerplate. We can make the compiler generate stuff for you. Cool. Item number 2, we actually have Lambda functions now. And that's, we don't have to write functor objects in C++ 11 anymore. We have Lambda functions. They're right there in your code. You can see exactly what they do. So what do I need to make up a visitor from Lambda functions? Well, yeah, there is implementation detail. Okay, I have to write this Lambda visitor thing. I'll show you what it is. I have to write this pet visitor. That's once per hierarchy, but it's actually auto-generated. Lambda visitor is written once per forever. And so, well, let's start with the easy part. Pet visitor. You write it only once. Why am I showing this to you? For the most part, I promised I'll skip implementation. I'm showing this to you because pet visitor captures the list of types that you could be using for visiting. We used to have this interesting pattern in C++, well, idiom, type list. Who remembers type list? Recursive template instantiation with a tail and recursive unwinding and all that stuff. Really impressive. Well, that thing is gone. Between the const expr if and the parameter packs, it's dead. This really is the type list. Type list is embedded in that ... here. This thing captures the type list. You will see later it does iterate over it. It does even better than that. I'll show you what it actually does. And it feeds that type list to whoever needs to process the types. That's the type list. Okay, so this you write once and forget about it. Here is the type list. Pet visitor is a visitor of cat and dog. By the way, classes cat and dog haven't been declared yet. No problem, that's forward declaration. You can do it. Second problem. Our visitor relies on overload resolution. We have all these overrides for all the concrete classes, and how do we visit a particular class? It's an overload resolution. Our Lambda visitor uses Lambda expressions instead of member functions. Lambda visitor should rely on overload resolution of Lambda expressions. You can't have overload resolution of Lambda expressions. Well, back to my favorite rule. If you can't have something but you really, really want to, you sort of can. So, okay, I'll skip this because I'll show you the cooler Lambda overload resolution. The previous one actually works in C++ 14. If you're in C++ 14, you have to use that one. You can find it in my slides. This is a cool one. Let's see, cursor. Template overload set inherits from its entire parameter pack. What does it do? These F things, they'll be lambdas. Lambdas have operator paren. I'm inheriting from all of them at once. which means I have injected all of these operator parens into my class, right here with this using, with dot, dot, dot. So now they're all available as member functions for overloading. So because I inherited from all my base classes, all these operator parens are now my member functions. Now the only thing is I have to generate the right overload set class from this template for my set of lambdas. And I do it like this. And this looks a lot like a function, like a template function that generates the right object by deducing from its arguments. It has arguments, it has template, it has a function name, it has auto-deduced return type, but it's not a template function. It's a C++17 deduction guide. Almost the same, not quite. It actually creates fictitious constructors that are the functions that are getting called and providing this thing. So these two lines are the overload resolution for Lambda expressions in C++17. You can't do it in C++14, but there is another one. You can find it on the slides if you want. So now, oh, by the way, see that little comma over there at the end? That's not a typo. This C++11 variant can handle it. Why would you want to do it? Okay, how many of you have reordered parameters in the function and then started to compile and had to go back and reorder the comma as well, the last comma? Who did that? Yeah. Well, minor thing helps to save time. Okay. So now, as I said, Visitor relies on overload resolution, but we now got overload resolution. Okay. So we have Lambda overload resolution. We have a type list hidden inside this pet visitor class. We have to iterate over the type in pet visitor and create the visitation connect, or basically channel the execution through. Now we have to create this Lambda visitor. Okay, I'm not going to show you the implementation. It's on the slides. It's lengthy, but you have to only do it once per forever. You write it once, not once per hierarchy. Once forever. You put it in your library and you instantiate it on your hierarchy. The interesting thing here, it has two type lists, one for the types, one for the lambdas, and it does, on the type lists, you had that zipper iterator. Iterates over two type lists in parallel, taking pair one at a time. Well, I told you the type list pattern is it's always gone. This thing iterates over two parameter packs, basically replacing that zipper iterator. Okay, skip that because it takes too long, but it will be in the slide. Oh, it is on the slide deck. It will be on the GitHub. You can look at the implementation. It's commented there. So now we get back to the client code. How does the pattern actually look like? That's the interesting part. How to implement it, you can figure out. How does the pattern look like? You know, if you don't know that you want to implement it, you can't figure out how to implement it. I'm showing you why you would want to implement it. One, type list. That's the pet visitor. I captured the types in the type list. Two, the visitable. You write it once per hierarchy because it's derived from the pet. And now comes your concrete stuff. Here is my derived class. Here is my visitor. Lambda visitor, again, you write it once per forever. Here is my visitor. You visit it exactly the same way as before. Okay, so what did I do? Well, first of all, you can now use Lambda expressions to create visitors instead of writing these visitor classes. Second, pretty much all the boilerplate plumbing is now synthesized by two templates that you write once per forever. And then you just instantiate them in one line like this, or one line like this, and the template instantiation generates all of that boilerplate for you. Much better. So this is actually a significant improvement. Boilerplate on visitor was honestly annoying. Again, this pattern has a twist. In addition to making things easier, there is also a making things new way. C++17 has an alternative to polymorphism, and that's the STD variant. It's also runtime polymorphism, just not using virtual functions. It also has something called STD visit, which is a very suggestive name. There's probably a way to visit something using STD visit. Yes, but it has its drawbacks, so you'll see what it looks like. Okay. First of all, here is our type list of visitable classes. Now, subtle difference here. They don't have to be derived from a common base. They are just classes now. They could be derived from a common base, but they don't have to. Other than that, the variant basically captures the type list of all the things I may want to visit. We did that before with our own type list. Now we're doing it with the std variant. Okay, I can wrap it in do visit, but basically this is the interesting part. std visit takes a visitor, which is just a callable right for him, and that variant. So if I have a pet, I construct the variant from the pet and visit it with the variant. Okay, here's my pet. Notice what's not here. The visitation interface is not here. There is no accept function anymore. Why? Well, there can't be because they're not derived from the same base, or don't have to be. Okay, common base is not required. How does my visitor look like? Well, here it is. Now we're back to that Lambda overload. That's the two-line Lambda overload that I've shown you before with the deduction guide. Lambda overload, here are my visitors, overloaded Lambda expressions, the ones you can't have. Type of that is, who knows, auto. So, classes I want to visit, and I visit them, basically I visit them, this function unravels to this line of code. C++17 visitor. Very compact, even less boilerplate, but you can wrap it in a function if you want. But you're not channeling your visitations through that accept method. Seems like a really good thing. I mean, who wants to write the boilerplate accept method? There is a price for that. There is a downside. And the downside is accept gives you a really easy way to write composite visitors. You have a class that has data members, you accept a visitor, and you just channel it to each. Visiting a family visits a cat, visits a dog. Well, who cares about the rest? Those are the important ones in the family. You can do that with the standard C++ visitor, including the Lambda visitor in C++17. That's just removing the boilerplate. You don't have that single bottleneck through which you can channel accesses in the std visit. Is that a problem? Well, it depends on what you're trying to do. If you're not writing composite visitors, it's not. But it's, again, it's a slightly different twist on the design pattern with different advantages and trade-offs. Well, that's a trade-off. So back to our original question. Does language development affect pattern use? There is a classic visitor. I also didn't show you a cyclic visitor in C++03. They're both unknowingly verbose to use. C++11 and 14 removes most of the unknowingly verbose part. C++14, and even better, C++17 lets you write visitors with Lambda expressions, which does what Lambda expressions normally do. Instead of a functor somewhere up there in your code down here, you now have your code. Basically, it's like you could write local functions. You can't write local functions in C++, but with Lambda expressions, basically you can. Okay, so much less friction in this pattern in C++17. The language C++17 didn't make anything huge to this. There wasn't any huge problem with it. It just was time-consuming, error-prone to use. There were lots of places you could make typos, mix up the types, and yeah, the compiler would eventually tell you. By the way, that override keyword that C++11 added, that's a godsend for this, because forgetting to override one of the functions is like the source of the most annoying bugs in this pattern. Okay, so much less friction. If you didn't use visitor before because you didn't like all the boilerplate, well, the boilerplate is gone. It's very easy to use visitor now. And there is a different visitor in C++17 which has its own trade-offs, very easy to use, has no overhead, no virtual calls, has some of the disadvantages of compared to normal one. Okay. Another mandatory C++ pattern, the ScopeGuard. The ScopeGuard has to do with giving away the punchline. The ScopeGuard has to do with exception handling. Forget what I said. With exception handling. Here is my database, I'm inserting a record. To the caller, it seems like either I'll insert a record, or if I can't, like it'll fail and nothing will happen. It'll just fail and database remains unchanged. Now, everything that I'm going to say, almost until the end, actually isn't about exception handling. The biggest mistake you can make in exception handling is to think about exception handling. It's all about error handling. You've got an unexpected condition, it's an error, you have to deal with it. Exceptions are a syntactic tool of dealing with it. They're nice, they have their advantages. Fundamentally, it's all about handling errors without getting into undefined state. So same problem if you returned an error code from this. It's not really about exception handling. It is about the transactional problem. Transactions are hard to do. My database isn't a simple class. It has a storage on disk and it has an index in memory. So to insert a record, I first write it on disk, insert it in the storage, and then I insert it into the index, and now I have a problem. If I fail to write to disk, it throws an exception. Again, may return an error code. I'll use exceptions for it. Throws exception, no problem. So far, so good. But if I succeeded to write to disk and then failed to insert into index because I ran out of memory, now my database is corrupted. I have unreachable record sitting on disk, and I don't know how to get that. No problem. Let's assume that you can undo writing to disk. You catch the exception from the index, and you undo the storage, and you rethrow the exception. Okay, now you got the transactional interface. And that was a pattern, I don't know, 15 years ago for using exceptions. Really annoying pattern. Again, exceptions are not critical. One of the problems you would run into is undo is honestly hard to do. It's hard to make your database that is like undoable forever. In reality, what you do is it's undoable for a bit of time, and then you have to finalize and commit. Maybe you have a buffer that sits before like you finally shove it into its permanent place on disk, and then undo and you commit the write. Okay, so you either undo and finalize, or you write, succeed, and finalize. Well, now we already have a problem. See, the finalize appears in two places. That's annoying. If you have 3 actions, it just gets progressively worse. See how the nesting grows. Well, that's problem number 1, the nesting grows. Problem number 2, bigger problem actually. It's not composable. What if I add action number 4? Where does the change go? Into the innermost part of the code. I don't just add it to the end. I have to stick it in here. It's not composable. Well, there is a pattern for that. Resource acquisition is initialization. In our case, it's more like resource deletion, but still called the same name. So I'm dealing with that double finalize call. Okay, I'll put it in the destructor of the storage finalizer. Whenever this object is destroyed, finalize will happen. So I created the finalizer. I don't have an explicit finalize. I may exit the scope through this row, or I may exit the scope through the bottom of the code. Either way, the destructor will fire, finalization will happen. Yes. So we did the finalize portion. Undo is still explicit, and if I wanted 3 of them, again, I would have to nested curly braces with the undos. So here is the one for 3. Cleanup, which is finalize, is now pretty nice. Rollback, which is undo, is still nested and scattered all over. But look at the cleanup part. Let's assume no error happens. Ignore the undo part. This is what the cleanup looks like. This is what the cleanup looks like. Not only it's nice and clean, but it's composable. If I want to add another action, I add the action to the end, add the cleanup to the end. I add the cleanup object to the end, which arms the cleanup action for when the cleanup finally needs to happen. And that's it. So now I'm composable here. Well, if I got the commit to work using the destructors, why can't I get the rollback to work doing destructors? Turns out I can. There is another pattern for that as well. Now I have a conditional destructor, which will normally fire the undo unless I disarm it. If I disarm the destructor, then undo won't happen. It's very similar to storage finalizer, except storage finalizer always finalizes. Storage guard may or may not undo. So this is what it looks like now. I'm going to try to insert into the storage. If it failed, nothing happened. If it didn't fail, I'm going to arm the cleanup action and arm the rollback action and try to insert into index. If that fails, both of the destructors will fire. Rollback will happen and finalizer will happen. If it succeeds, I have to quickly disarm the rollback because I don't want it to happen now. And the finalizer will still fire. No try-catch blocks. I never catch anything except when I want to finally stop it from propagating. This style of programming, by the way, called declarative programming. You state your intent. I want to finalize, and I want to roll back if an error happens. That second part isn't quite declarative yet, but it'll get better. It'll get better when we get to C++ 17. Okay, what's the problem with that? By the way, everything so far was C++ 03. You have to write one of these for every commit and rollback and any other action you want to arm. There is a lot of boilerplate in it. They're not easy to write. In fact, this one is wrong. Why is this one wrong? What happens if you copy one of these?
Because you're holding a reference.
Really bad things happen if you do. So that one is wrong. Now, this is C++ 11 version. You can do a 3 version of blocking the constructors, the copies. Okay, so now we get to what I really want. What I really want is something that looks like this. I want to have the ScopeGuard, which is generic, and I arm it with a finalize action. The call finalize on S. And another one that call undo on S, unless I disarm it by calling commit. Now that's kind of what I want. What I really, really want is I want to know if I am exiting the bottom of the scope by throwing an exception or not. And if I'm exiting by throwing exception, then I had a failure, and I want the rollback to happen. And if I'm exiting by normal return, then I didn't have a failure, and I want the rollback to not happen. And I don't want to commit explicitly. Now, of course, this presupposes that all my returns are successes, and all my exception throwing are failures. If that's not true, then of course this idea doesn't work. Okay, so implementation is on the backup slides that will be in the deck. Well, they are in the deck that you can download. The client side, the client view. The client view is more important than the implementation. Implementation you do once. The client view is what you live with. There is this mildly annoying base class that you have to know what it is because it's not normally visible anywhere else. There is this make guard function, and by the way, I'm cheating here. The way this is written, it's not actually calling a member function finalize on the object S, it's calling a global, or undo. It's calling a global function undo that I use to wrap the member function S. You can make a member function call. It's slightly more annoying than this. Oh, and it has fixed number of arguments. One object and one member function or non-member function to call on it. And it has an explicit commit. And in C++ 03, that's the best you can do. You can wrap it into macros, make it a little nicer, but fundamentally that's the best you can do. Okay, let's skip the implementation. Okay. Comes 11 with variadic templates, comes 14 with the return type deduction, comes 17 with constructor type deduction. You can get rid of a lot of these problems, but honestly not enough. You can optimize, improve that scope guard that I've shown you using C++ 1x features. Don't. Still ugly. There is a radical change. This one, the reason I'm showing you this pattern is because it has probably the most radical dramatic change of all patterns that I know in the evolution of language from 03 to 17. Okay, this is the 14 scope guard. I still have the make guard, don't have the base type anymore. And I don't have the arguments. I just put Lambda functions in there. If I want to call member function, I call member function. If I want to call 5 member function, I do that. However, if I want to pass arguments in, I can, but normally it just captures the variables from the outside, which is normally what your scope guard needs to do anyway. Still explicit commit on the bottom. So automatic variable capture, very good. No limitations on the number of arguments or what you can call or what other code you can stick in that scope guard. Very good. Automatic commit. I mean, a manual commit, sorry. Manual commit. Not quite. Okay, C++ 17. Make guard is gone. We have the deduction rules. That the template argument deduction that the make guard template function used to do. Now constructors do that in C++ 17. Okay, and I could get rid of the commit if I promise that all my returns are successes and all my exceptions are failures. Let's say I do that. Okay, skip the implementation. Okay, so this is how my code looks like. In C++ 17, this is a scope guard. Action, arm cleanup, arm rollback. Action, arm cleanup, arm rollback. You want third one, fourth one, nth one, just add, you keep adding these 3 lines, as many as you want. It's perfectly composable. If you do manual commits, you have to do all the commits at the end. If you don't, the last lines go away. Okay, so what about the automatic rollback? Automatic rollback is very simple. We have std uncaught exception. If we're exiting this bottom, the scope, we're passing through this curly brace, with uncaught exception true, exception was thrown and we're in a failure state. If we're not exiting it with uncaught exception, return was called and we are in a success state. Right? Not quite. Unless we entered that entire sequence of code with an exception already in flight. And why would we do that? Well, if that entire chunk of code is in an exception unwinding channel. But, you say, you can't have second exception thrown in an exception unwinding channel. Not exactly true. You can have as many thrown as you want. You can only have one propagating, which means you would, if there could be exception in flight here, and you want to be able to throw one here, you have to cache it. But in this code, in here, many exceptions can be flying at the same time. As long as you only let one of them escape, you're fine. Which means if you arrive to this point and the exception is in flight, you actually don't know whether you succeeded, whether you failed or somebody else failed. And if somebody else failed, it's their rollbacks that are being armed. You succeeded, your rollbacks should be disarmed. Which is why in C++ 14 you can't have automatic commits. Comes to C++ 17. They replaced uncaught exception with uncaught exceptions. Make sure to highlight it in red, that's how the compiler knows it. Now, this tells you how many you had on input and tells you how many you have on exit. If you added one more. Now again, how could you add one more? Well, this whole thing is not necessarily escaping yet. You may still be inside the try-catch block. So just the scope with the curly braces, you can exit through it with multiple exceptions. It's just you can't exit the function. So you could have a try-catch block outside of these curly braces and not let the exception escape the function call, and then you're okay. So in general, you don't know how many exceptions were before, but you can ask. If nothing failed here, however many exceptions were in flight when you started this, that's how many you end with, which means you succeeded. Somebody else is failing badly, but you succeeded. Your rollbacks should be disarmed. If you added one exception to it, somebody else may or may not be failing, but you failed. Your rollbacks should fire. Okay, so composable automatic exception detection. So, well, the answer here is obvious. Yeah, language development fundamentally affected the pattern use, hugely. Now, note this point. You can have automatic rollback if you decide to constrain yourself to always using exceptions to signal failures. It's a very nice composable commit and rollback. Really nice, exception-safe, error-safe, exception-safe coding style. Would that be enough if you didn't make that decision before about only throwing exceptions for failures, making all return successes. That's almost bulletproof exception safety. Would that benefit be enough to make you switch to use exceptions? Maybe. I mean, I'm not saying it always is, but it's something you should be seriously considering. You could be prompted to change the way you handle failures based on how reliable this pattern became in C++ 17. Yeah, let's skip that one. It's not a particularly interesting pattern. So, do design patterns depend on the language? Fundamentally, no. If you look at the pattern in isolation, not really. But you never look at the pattern in isolation. You have a problem to solve. You have a complex problem to solve. That complexity has to be somewhere. Where exactly you're going to bury it and how it's going to look like. The subtle trade-offs between multiple ways to solve that problem, those are influenced by language evolution. So the kind of what I want you to leave with is this notion that the annoyances, the copy pasting, the boilerplate code, all the overhead, all the friction that you're used to, if you get access to a new version of the language, think it over. Think if you can remove it from what you're doing. But also, if you can remove it from a different design pattern that solves the same problem, but uses a different design. Maybe you can make your code a lot better by redesigning, because another pattern you earlier considered it and dismissed it because it was too hard to use. Maybe it's not that hard to use anymore. And if you want to know more about patterns, well, stay here, I'll show you the code, ask me, and I'll read my book. Thank you. Questions? Well, if there are no questions, thanks again. And oh, sure.
Does the pattern you describe are printed in your book?
Which one?
The pattern you describe are printed
Everything except the builder. The builder is not in my book. I can point you to the book which has that builder. Everything else is in the book. Lambda overload, named arguments, which I briefly mentioned. They have a chapter. It's not really a pattern, it's a C++ idiom, because some languages just have it. But that idiom is in my book, yes. Yes?
Yeah. Do you feel that with the Lambda expression and that, let's say, new style, it make it harder for a developer to read that and understand what is the intent and the design pattern behind compared to the boilerplate?
I actually think that for the most part it's easier, because the biggest problem with the functors was it was hard to know what that functor does.
Yeah.
The code is scattered. Here it's, with the lambdas it's basically like, here is my code, here is my variables, do this line to my variables. It's, for the most part, I mean, yes, it can be abused. And Lambda expression syntax can be very terse if you omit all the things you can omit, and I'm kind of guilty of that, but I have only so much room on the slides. Lambda syntax can be a bit cryptic until you get used to it. But setting that aside, and you can make it actually, you can spell it out, you can leave all the parentheses where they need to be and all that. You can make it verbose. The fact that the code is right there and visible, I would say for the most part, it's a disadvantage. I mean, it's an advantage, sorry, it's an advantage, it's a benefit. Now, one advantage you had before is your functors had names. The names could be expressive. But that's not entirely gone. Let's see, where are... Well, it would be in the visitor. See, that's not entirely gone because, but by the way, this doesn't have to be local. If you want a global, like let's say you want to have a functor that you use in many places, you can have this outside of your local scope, this chunk of code with an auto, and it would work. So this name basically replaces the functor name. So if you had if it was a globally useful thing and you had a meaningful name for it, you still do it.
Okay.
But if it was one-time use, local, just basically you needed this dispatch, it's right there. You can see exactly what it does.
Okay. Otherwise, you said that these example will be on GitHub.
Sorry. Well, the slide deck will. I mean, the conference puts the whole thing on GitHub.
Yeah,
now, by the way, again, except the builder, most of these came from my book, which has fully compilable code on GitHub from the publisher, and I can point you to that if you want. So so the book has snippets, of course, but I have like fully compilable version of it hooked up to, like if the tests are needed, to Google test, if it's just an example to an example, if it's a benchmark to Google benchmark, and so you can run it and basically see what it does, including this one. So I have fully compilable version of this in the GitHub for my book. You can download them.
Where do we see that? The fully compiled version?
Okay, well, I didn't put up the URL for this. So, okay, that was on the first slide. Okay, so if you buy my book, it comes with a reference to the GitHub. If you don't buy it, you can still go to the GitHub and download it, and I'll just stop by and I'll show you where.
Okay. Thank you.
So, which book has the builder pattern?
The builder pattern, there is a book by Dmitry Nesteruk. Let's see. Again, come to me right after. I'll fire up the browser and point you to it.
So the title is Design Patterns in Modern C++.
Well, the title of the book? Oh, you mean that book?
Dimitri's book.
Yeah, Dimitri's book. Well, it's probably easier to find by name because lots of books with design patterns and C++ searches kind of go all over the place. But I'll show you by name. Yeah, that one has the builder.
What's the pattern that you use the most?
Talk into the microphone.
The question was, what's the pattern that I use the most? What's the pattern that? Well, if you just count the uses, probably it would be some sort of factory. There are kind of many different flavors of factory. So if you combine together like the factory, the abstract factory, and the prototype, which is just a way of like factory cloning a class from another, or not necessarily cloning exactly, but given a class, construct something from that class. If you combine all three of them that look like factories into the factory, would be that one. For probably, like if nothing else, if you have a polymorphic hierarchy and you want a copy of one of those objects, well, that's how you do it. You have basically a virtual clone. Sometimes it's called virtual constructor. There is no such thing as virtual constructor. Sometimes in C++ that pattern is called virtual constructor, but it's basically a factory that makes a copy of a polymorphic of the object. You have the base pointer. You want a copy of whatever that thing really is. Well, you call a virtual clone and it gives you the copy. That's basically it. You wrap it in some nicer syntax, but basically that's what it is. And that's a kind of factory too. So if you count all the factories, I would say factory. Depends on the domain. So I work on graph analysis code a lot. There, definitely the visitor. Everything we do is, apply this visitor to the entire graph, like visit every node, do stuff. We have dozens of visitors and just one graph. And we keep adding visitors. So in that domain, visitor, for sure. Okay, well, thank you everyone again and questions. And as I said, I'll be available for any.